At the edge of our solar system, 4.5 billion kilometers from the Sun, so far that sunlight takes 4 hours to reach it, there is a world that should be dead. It receives 900 times less solar energy than Earth, 1/900th. At that distance, Neptune should be a frozen ball of ice, silent, still, a corpse drifting through the void. But instead, Neptune is the most violent planet in the solar system. Wind speeds reach 2,100 kilometers per hour. 2,100, that's 1.5 times the speed of sound, faster than a fighter jet, faster than a bullet train, supersonic winds that tear across the planet's surface in storms the size of Earth itself. And here's what defies all logic. The farther you get from the Sun, the slower planetary winds should be. Jupiter's winds, 640 kilometers per hour. Saturn's, 1,800 kilometers per hour. Uranus, closer than Neptune, only 900 kilometers per hour. But Neptune breaks the rules. Tonight, you're going to discover why the farthest planet is the most violent. Why a world that receives almost no energy from the Sun generates the fastest winds ever recorded. And when you understand the nightmare mechanism driving this planet, you'll realize that Neptune is powered by something far more terrifying than sunlight. It's powered by its own death. August 25th, 1989, NASA's Voyager 2 spacecraft makes humanity's first and only close approach to Neptune. After a 12-year journey across 4.4 billion kilometers, flying past Jupiter, Saturn, and Uranus, Voyager 2 finally reaches the last planet. Scientists expect a quiet ice giant, a cold, sluggish world where weather moves slowly, if at all. What they found made them question their instruments. The Great Dark Spot, an anticyclonic storm system 13,000 kilometers across, the size of Earth, with winds at its edge clocking 2,400 kilometers per hour. 2,400, that's Mach 2, twice the speed of sound. For context, Hurricane Katrina's peak winds were 280 kilometers per hour, the strongest tornado ever recorded on Earth, 486 kilometers per hour. Neptune's winds are 5 times faster than the most violent weather on our planet. But here's where it gets incomprehensible. Neptune is 30 times farther from the Sun than Earth. It receives 0.1% of the solar energy Earth receives. 1,000th. At that energy input, the mathematics of planetary atmospheres says Neptune's winds should barely move, maybe 50 kilometers per hour, 100 at most. Instead, they're supersonic. Voyager's images showed something else. The Great Dark Spot was moving, rotating, and above it, in Neptune's stratosphere, there were white clouds, frozen methane crystals being torn upward by the violence below, 50 kilometers above the main cloud deck. Weather so violent it was launching material into space. And then scientists calculated the rotation period of these storm systems. The Great Dark Spot rotated every 16 hours, but Neptune itself rotates every 16.1 hours. The storm was rotating faster than the planet beneath it. The winds were overtaking the planet's rotation. How? What kind of energy could drive this? Let me explain the nightmare equation that powers Neptune. Every planet generates some internal heat. Earth does, Jupiter does. This is usually leftover heat from the planet's formation, primordial heat from 4.5 billion years ago, when the solar system was born, slowly leaking out over billions of years. But Neptune radiates 2.6 times more energy than it receives from the Sun. 2.6 times. For every unit of solar energy Neptune absorbs, it emits 2.6 units back into space. Where is that extra energy coming from? The answer: Neptune is contracting, slowly, inexorably. The planet is collapsing under its own gravity. As it contracts, gravitational potential energy converts to heat through a process called Kelvin-Helmholtz contraction. Neptune is literally squeezing itself, and that compression generates massive amounts of heat. Scientists calculated the numbers. Neptune's internal heat output is approximately 4.3 trillion watts. That's 4,300 terawatts. To put that in perspective, human civilization uses about 20 terawatts of power total. Neptune generates 200 times more energy than all of humanity combined from collapsing. And this heat doesn't distribute evenly. It rises from the interior in massive convection cells, columns of hot gas surging upward like volcanic plumes, then cooling and sinking back down. These convection currents are violent. They create temperature gradients, pressure differentials, instabilities. And that drives the winds. But here's the existential horror. This process will continue for billions of years. Neptune will keep contracting, keep heating itself, keep generating these supersonic winds. Long after the sun becomes a red giant and consumes Earth, Neptune will still be out there in the dark, contracting, heating, howling with winds we can barely imagine. Neptune is a planet eating itself to stay warm, and the screaming winds are its death rattle. 1994, the Hubble Space Telescope turned its gaze toward Neptune to follow up on Voyager's observations. Scientists wanted to track the Great Dark Spot, study its evolution, understand its mechanism. But when the images came back, they found nothing. The Great Dark Spot was gone, vanished, disappeared in less than 5 years. A storm the size of Earth, with winds over 2,000 kilometers per hour, had simply dissolved. At first, scientists thought it was an error. They searched the images, ran the data again, but it was confirmed. The storm had dissipated. And then they found something worse. A new dark spot in the northern hemisphere, different location, different size. Neptune had created a replacement storm, and this wasn't the last. Hubble has now observed Neptune for 30 years, and dark spots appear and disappear like clockwork. Sometimes there are multiple storms at once, sometimes none. They form, rage for a few years, then vanish as if they never existed. Neptune doesn't have stable weather patterns like Jupiter's Great Red Spot, which has persisted for centuries. Neptune's weather is chaotic, unpredictable. The storms are born and die on timescales of years, replaced by new storms in different locations. Scientists tried to model this. They couldn't. The dynamics were too complex, too violent, the convection too powerful. Neptune's atmosphere operates in a regime of physics where our models break down. In 2019, a team used advanced climate models and thousands of hours of supercomputer time to simulate Neptune's atmosphere. They discovered something disturbing. Neptune shouldn't be able to maintain these wind speeds. The sheer forces should tear the jet streams apart. The turbulence should dissipate the energy. But instead, the winds are accelerating. Hubble observations from 2023 showed wind speeds increasing over the past decade. Neptune's winds are getting faster. Why? We don't know. Let's descend into Neptune's atmosphere and understand the structure of this nightmare. The visible cloud layer you see in images, that's not the surface. Neptune doesn't have a solid surface. It's an ice giant, mostly water, methane, and ammonia ices surrounding a small rocky core. What you see is the methane cloud deck at an altitude where temperature and pressure allow methane to condense. Start at the top, the stratosphere. Temperatures here reach -218 degrees Celsius, cold enough to freeze methane solid. But because of the violent updrafts from below, methane gets pushed up into the stratosphere where it freezes into white clouds, like shrapnel being ejected from explosions. Drop down into the troposphere. This is where the main weather happens. The blue color you see, methane absorption of red light. But beneath that picturesque blue, winds are tearing across latitudinal bands at different speeds. The equatorial region moves at 400 kilometers per hour. Mid-latitudes, 1,200 kilometers per hour. the highest latitudes 2,100 kilometers per hour. These different wind speeds create shear zones, boundaries where adjacent atmospheric layers are moving at different speeds, grinding against each other like tectonic plates. And at these shear boundaries, turbulence, vortices, storms. Keep descending. At 80 kilometers depth, pressure reaches 10 atmospheres. Temperature rises to 0 degrees Celsius, the freezing point of water. But you're not in water. You're in supercritical methane and ammonia. The pressure is so high, these substances exist in a state between liquid and gas. Continue to 200 kilometers. Pressure, 50 atmospheres. Temperature, 1,000 degrees Celsius. The ices aren't frozen anymore. They're liquid, hot, convecting violently. And deeper still, toward the core, pressures reach millions of atmospheres. Temperatures exceed 5,000 degrees Celsius, hotter than the sun's surface. At these pressures, carbon in methane breaks down and forms diamond. Scientists believe it literally rains diamonds on Neptune, falling through the superhot liquid layers toward the core. But you'd never reach the diamonds, because at 50 kilometers depth, the winds would have torn you apart. At 100 kilometers, the pressure would have crushed you. At 200 kilometers, the heat would have vaporized you. Neptune is layered violence, all the way down. But Neptune isn't alone in its violence. It has a companion, a victim. Triton, Neptune's largest moon, the coldest object ever measured in our solar system at negative 235 degrees Celsius. A frozen world with nitrogen geysers erupting from its surface, shooting material 8 kilometers into space. But here's what makes Triton unique. It orbits backwards, retrograde, the only large moon in the solar system that orbits opposite to its planet's rotation. This tells us something horrifying. Triton isn't Neptune's moon, it's Neptune's captive. Triton was once a Kuiper Belt object, a dwarf planet like Pluto, orbiting the sun peacefully in the outer solar system. And then, perhaps 3 billion years ago, Triton passed too, close to Neptune. Neptune's gravity captured it, pulled it into orbit, but the orbit was chaotic, elliptical. Over millions of years, gravitational interactions with Neptune's other moons circularized Triton's orbit, but left it retrograde. And now, Triton is doomed. A retrograde orbit is unstable. Tidal forces between Neptune and Triton are slowing Triton down. Every orbit, Triton drops closer to Neptune. In 3.6 billion years, Triton will cross the Roche limit, the distance where Neptune's gravity will overcome Triton's own gravity. And Neptune will tear Triton apart, shredded into a ring system more spectacular than Saturn's. Triton will cease to exist as a moon and will become debris orbiting Neptune. Neptune captured a dwarf planet, imprisoned it in a backward orbit, and is slowly pulling it to its death. This is the nature of the outer solar system: violent, unforgiving, chaotic. And Neptune sits at the center of it, with its supersonic winds and collapsing core. A predator howling in the dark. Right now, 4.5 billion kilometers away, Neptune is rotating. Every 16 hours, the planet completes one turn, and across its surface, winds are screaming at 2,100 kilometers per hour. Dark spots are forming, dissolving, reforming in new locations. Methane clouds are being torn upward. Diamond rain is falling through superheated liquid. The planet is contracting, squeezing itself, converting gravitational energy into violent convection. We will never send another probe to Neptune in our lifetimes. Voyager 2's flyby was our only close look. Everything else is telescopes, models, speculation. Neptune remains a mystery, a violent, howling mystery at the edge of the solar system. And the farthest planet is the most dangerous. Not because of what it receives from the sun, but because of what it generates from within. Neptune doesn't need the sun to be violent. It needs only itself.